That's really important. That's a really important step that I completely missed. Okay, so now we even have both the recording and the stream. All right, so for the people who are joining us in the future, let me briefly recap what's happening here. So first of all, we assume that k is greater than 0. The dimension of our manifolds is 0, i.e. we consider just configurations of points. And we make a claim about, first of all, the group of, or rather the monoid of components for this topological monoid. And we also claim that the classifying space for this monoid is homotype equivalent to the component, or rather weakly equivalent to the component of the empty manifold in this H space. So now I recall the definitions of everything here. So so this is the H space of configurations of points in a cylinder of the form the interval, the unit interval to the power of k times r n minus k. So the product structure is given by juxtaposition in well, just by juxtaposition. So we take configuration, we compress this first k coordinates so that they actually fit into the product of half intervals, and then we put two configurations side by side, and we obtain a new product configuration. And M and K similarly is the Mooreization, so to speak, of C and K. So now an immediate corollary of this proposition, if it's true, is that C and K is homotype equivalent to the loop space of C and K plus 1, because for group-like monoids, i.e. when the group of components is a group, not just a monoid, we have an equivalence like this. Last time I even provided a reference to a certain theorem of May, which explicitly exhibits M, or rather the loop space on PM, as the fiber of the classifying vibration, which is constructed using certain simplicial model for both the total space of the universal bundle and the classifying space. And it is the key result of May that for group-like monoids, this map between these specific models is not just any map, but quasi-fibration, meaning that its geometric fiber is weakly equivalent to its homotopy fiber via the inclusion map. So this is the result of May from 1975. You can find it either in his book on classifying spaces, or you can find proper reference in my notes. All right, so of course, this is tremendously important, because then we can consider a sequence of maps like this, and so on. And we terminate at omega n Cn, which, as we saw, is homotype equivalent to Sn, which shows us that actually we have an equivalence between, for example, the homology of the infinite configuration space and the homology of the infinite loop space. So this is really the crux of the Madsen-Weiss theorem in dimension 0, or the Barrett-Pretty-Coulomb theorem, as it is known. So it's a better known name of this result. So in this case, it's the configuration space of of infinitely many points in R infinity. So rather, it's a co-limit of the configuration spaces of endpoints in R infinity, which itself is a co-limit of the configuration spaces of endpoints in Rm. Okay, so after this quick recap, let's formulate a key lemma, which is essential for the proof of this proposition. So first of all, pi 0 of C and K is equal to 0 when K is greater than D. So in our case, it's all the time because D is 0. And this means that we can discard all the other cases considered in Fletcher. So let's prove this lemma. So first of all, observe that the point in C and K is a configuration C in Rn. And moreover, the projection from C to Rk, so the first K coordinates, is a proper map. Here it's really a nonsensical condition, because obviously a map from a finite set of points to anything is proper. So that's quite clear. And if K is greater than the dimension, in this case 0, then we assume that P is transversal. So we assume transversality of P. Then the preimage of some specific point is, for a transversal map, an empty set. So
one question. By configuration, you mean ordered or unordered? Which one do you mean? I guess unordered, right? But I mean, if because last week I remember you took unordered configuration, but okay, so in this case, this map P is not well defined. Am I mistaken?
One moment. Let me think for a moment. What do I really mean by this?
I think here all configurations are unordered. Is this correct?
Yeah, probably yes, because yes, in our setup all configurations are unordered, and I guess the quickest way to see this is to recall the general construction of C and K for manifolds of arbitrary dimension. We consider just the space of embeddings into Rn, and then we mod out by the group of orientation preserving diffeomorphisms of M. So it will be more appropriate to call it C and K of M. And in our case, obviously, all automorphisms, all a set of points are orientation preserving. So in our case, we consider unordered configurations. Thank you for this question.
Thank you.
It's really important to really keep track of what's happening here. Okay, so the fact that 0 is transversal to P means that there is a certain ball which contains 0, such that the image of this configuration intersected with this ball is empty. The map is proper, and it's basically for us it's a complete triviality because our set is finite, so we can take the minimum divided by 2 of the distance from 0 to the points of the image.
Richard, just a small typographic remark to denote two things being transversal. People normally use an arc with a vertical bar through it. Трансверсальность обычно обозначается, значит, так, значит, рисуется дуга и через нее вертикальный ход. Exactly. This is.
It was just some deformation that this letter suffered in my hands. Yes, this is the standard notation indeed. Yeah, I meant this sign, of course. Thank you for this correction. All right, so after finding this ball, we can just rescale RK can be rescaled from 0 so that H. This is the maybe an unfortunate notation, but by this I mean the homotheta centered at 0 with factor lambda. So the image of the ball is the whole RK. So, or maybe rather instead maybe I should write it something like this. So we take a segment from 1 to infinity, and we take the union of images of these balls under rescalings or homotheties, and we obtain the whole space. So this means that we obtain a path from C to the empty set. So to be frank, we only did it in some projection, but we can take a product like this. So the last n minus k coordinates remain fixed, and we rescale like this. I'm not sure that this is correct, actually, because to me it seems that we're losing this condition that our configuration is bounded by these conditions on the first k coordinates. So
What do we do exactly when we rescale? Do we rescale along all coordinates or just some coordinates?
So the idea is that we expand this factor Rk. So supposedly the image of the configuration should actually lie in this, if I'm not mistaken. And clearly a rescaling of this does not preserve this condition. So that's my confusion with this argument.
По-моему, там каждый раз
Oh, no, the confusion vanished. I'm sorry. I just messed up the notation. That's.
Мы раздуваем не все координаты, а какие-то из них.
Не, там проблема была в том, что я перепутал k и n минус k, и мне казалось, что k координаты как раз ограничены, а они на самом деле не ограничены. Все хорошо. Okay, so let me explain what happened. So I mistakenly assumed that the elements of C and K belong to this, while in actuality they belong to sort of the opposite space. So now it's completely clear what happens. So we can rescale indefinitely in the first k coordinates, fixing the last n minus k coordinates, and obtain a path from our configuration to the empty manifold, to the empty configuration in our case. So the path, and hence we see that phi 0 of C and K is 0 for K greater than 0. So here you can see that it is essential that we have at least one unbounded chord. Otherwise, we can't really rescale anything, and this argument fails. So is it clear? Is it making any sense?
Richard, I'm sorry. Could you please remind me and maybe the others too? What are we trying to prove at the moment?
So for now, we try to prove the following innocently looking lemma that this thing is connected.
Okay, and what's the next goal?
So the next goal is to prove the following proposition, which asserts that for well, somehow we should get this case as well, but for now, for k greater than 0, first of all, M and K is a group-like monoid, and second, the classifying space of M and K is equivalent to the component of C and K plus 1, which contains the empty configuration.
Okay, so we already know this for K greater than 0, and we want to prove this for basically if D is 0, then we want to understand why the case K equals 0 is no different from K greater than 0. Is this correct?
Yes, yes, but for now, I only understand I only understand the words in the argument. I don't understand the essence, so I can't really say why this works. But I will try to present the argument, and hopefully we will see how the case of k equal to 0 is indeed no different from the case of positive k.
Okay.
So, oops. So proof of the proposition. Okay, so let's take BM and K, and we want to show that we have an equivalence like this. So first of all, I made a feeble attempt at this last time. We want to define a map from B, M, and K to C and K plus 1, which will at least somewhat be a candidate for this equivalence. So then we will show that it is a weak homotopy equivalence using certain argument about classes and homotopy groups. So assume that we have a point P in the classifying space. Then this point corresponds to the following datum. So first of all, we have M1, etc., MQ, which belongs to, so these are the points of this monoid. And we also have the following collection of barycentric coordinates which present a point in a topological simplex. So obviously the space DM and K can be presented using the skeletal filtration on a simplicial set or a semi-simplicial set. And each point belongs to a certain simplex. Well, it may belong to many simplices, but we have so we have the simplex such that this point belongs to its interior. So Q is the number, is the dimension of this simplex. All right, so we can take a product of these points in our monoid, and we can obtain so this point corresponds to a configuration. This point corresponds to another configuration. So we have two configurations. And we know that K plus first coordinate of this product. Coordinates of CIs belong to the following collection of segments. So these are just certain fixed numbers that appeared in the definition of the Mooreization of the H space C and K. So remember that M was constructed as a subspace of C. I don't specify indices, but it's quite frankly irrelevant here. So we took a product like this, and then we specified a certain subspace which corresponded to and juxtaposition product of manifolds. So we have the following chain of inequalities, and we can take the product of all configurations and obtain another configuration which sits in Cn k plus 1. So observe that moment. Let me think what actually happened here. Well, yeah, the thing that happened here is that basically we assumed that Ci belonged to M and K, which meant that Ci was presented by denoted like this. So it was presented by something like this, where AI was, I guess, less than 1. And then after taking the product like this, we sort of spilled out of this monoid, because now we don't have any such restriction on the k plus first coordinate. So let me just very quickly verify that I don't say anything incredibly stupid here. So so I'm sorry. So let me just rigorously define M and K here. It's important that we remember this. So M and K actually consists of pairs CA, such that C is a configuration in RK times 0A times 0, 1, and minus k minus 1. So here we don't have any restriction on A. It can belong to just the whole set of non-net reals, and it means that indeed, when we take a co-product like this, our k plus first coordinate of the resulting configuration is not restricted by 1, is not bounded by 1, which means that we actually end up in Cn k plus 1. So this is a rough idea of how we can obtain a point in Cn k plus 1 from a point in the classifying space of the monoid M and K. So we just take the juxtaposition product and we obtain something in Cn k plus 1. So what's possibly wrong with this construction? Well, first of all, let's look closely at what happens in the degenerate cases. So we have a pair which consists of a collection of points in the monoid and barycentric coordinates. So obviously, if either W0 or WQ tends to 0, which means we go to the face of a simplex, the face of the simplex, it means that C1 or CQ vanishes. And moreover, C without C1, so this coproduct without C1, the remaining union of configurations moves by A1 to the right in the K plus first coordinate. So why is it this happening? Well, simply because when we don't have A0, which is equal to 0, the starting point is now A1. So the whole thing moved, which is completely unacceptable. And this happens obviously when the barycentric coordinate with index 0 tends to 0. And of course, this can be remedied if we say that, okay, well, A0 shouldn't be necessarily 0. This is just some artificial restriction, and we can now assume that we start. We can now assume that the barycenter of these points AIs actually always is 0. So our points are sort of balanced around 0, which of course means that if one of the weights tends to 0, then the condition is still satisfied because, well, we just lost one of the summons, but all the remaining summons compensated, and the barycenter is still at 0. So now we want to fix this problem with the vanishing manifolds or vanishing configurations. And to do this, we use the following construction. So we construct the lower and upper barycenters. And what that means is that actually, if we have a barycenter which is B, we can just take each point on this line into either AI plus, which is the maximum of AI and B, or AI minus, which is the minimum of AI and B. And if we think of it as so if we think that the barycenter is always fixed at 0 by our assumption, actually what that means is that, okay, we have a collection. So, okay, we have a collection of points A0, maybe A1, A2, and barycenter B, which is 0 secant. And then if we take the plus picture, this means that now A0 plus is at the same place as B, and A1 plus coincides with A1, and A2 plus coincides with A2. So what happened is that we just sort of moved the sole negative point to 0. And similarly, if we consider the lower barycenter, then we obtain A0 minus, which coincides with A0, and then both A1 and A2 minus coincide with B now. And now the B plus is just the barycenter of this new collection of points with the same weights as the initial collection, but now some points moved to the original barycenter.
Сейчас, Гриша, если честно, вот это основной, this is the main technical part of the proof, and it's also the most obscure part of the proof. So let's have a look at the picture in more detail. So suppose we have 3 points, A0, A1, A2, and what are the classes?
Sorry.
Значит, понимаете ли вы геометрию происходящего?
No, я понимаю, что происходит. I understand what's happening, but I don't understand any intuition behind it.
So let's try to figure it out. By the way, Philip, Savan, do you understand what's going on?
Yes, I sort of did, yeah.
Philip.
My answer is similar to Grisha's.
Okay, so let's at least go through this again, because at the moment I sort of understand what we're after, but I'm not able to relate it to the formulas.
Yeah. So maybe a good idea is to see the rest of the proof and understand what properties of these two new barycenters we use in the proof. So my idea is that this is some kind of technical construction which just satisfies certain good properties, and it can be done in a different way, and just this is the choice that Hatcher made when he wrote the notes. So I'm not sure that it's something fundamental.
Okay, well, let's check whether or not your understanding of what's going on and mine are the same. So suppose one of the weights goes to 0. And then the leftmost component escapes to infinity. And moreover, it does so so we push it away in the k plus first coordinate. does this coincide with your understanding? Значит говоря, когда W0 стремится к нулю, компонента, значит, левая компонента по координате k плюс 1 уезжает на бесконечность. Соответствует ли это вашему...
Почему?
Она хочет избавиться в таком случае от самой левой компоненты, правильно?
Да.
Вот. Значит, как мы от этого избавляемся, мы увозим ее на бесконечность. Еще не очень понятно, как это называется.
Я просто не понимаю, где это написано. I just don't understand where this comes from. So it sounds like a nice idea, but I don't understand why is this what's happening really.
Well, that's the question. Hatcher doesn't mention it explicitly. This is what seems to be happening. Let's try to figure out whether or not this is indeed what is happening.
Okay, maybe let's try this. So, I mean, the thing is that I understand this W going to 0 very formally, so I just think of simplices in the classifying space as being labeled with, say, I don't know, M0, M1, M2. Maybe that's not. Sorry, incorrect notation. M1, M2, and this is the composition M1, M2. And then when one of the coordinates goes to 0, I just think of it as just looking at the classified space and taking a face which contains strictly smaller number of manifolds
Then we need to make sense of the statement that the limit of a point on the face of dimension something is a point on the face of dimension something minus 1.
But that's sort of the definition of the barycentric coordinates, isn't it?
Yes, and well, the vertex amongst the vertices, one of the vertices is now missing. So we want to get rid of this of the corresponding manifold in a continuous way. The question is how we do this.
Yeah, but I guess what you're saying is sort of the answer to how to construct a continuous map. For now, it's we don't have a construction, so maybe I should write down the formulas that Hatcher uses, and then we can sort of see what you're explaining from these formulas.
Okay. Well, let's write the formulas and see if we can figure out the geometry behind the formulas. We may or may not succeed.
Yeah, that sounds like a good plan. So let me do this. Okay, so we have inequalities like this, which are quite obvious. That the smallest coordinate A0 is less than or equal to B minus, which is itself less than or equal to B, which is itself less than or equal to B plus, and then it is all dominated by the last coordinate. So the last bounding, this I don't know how to call it. Well, the last estimate on the k plus first coordinate of the configuration CQ. So if so either all of them are sharp, so all of them, by them I mean these inequalities, or all of them are equalities, and then this means that the configuration is just an empty configuration. So far it seems quite trivial. I don't know. So now let's define this map and see if this description via deletion to infinity coincides with the formula which is used here. So the map looks like this. We take M, which belongs to the following slice S from B minus to B plus, which itself is equal to RK times B minus B plus times R n minus K minus 1. So now we can, maybe, yeah, so now let's rescale as B minus B plus to S minus infinity. As infinity, which just coincides with Rn. Or more explicitly, we have a linear map from Rn to Rn. Sorry, we have just a map from Rn to Rn, which rescales minus infinity plus infinity to the canonical interval -1 plus 1. And then we have a linear map which rescales it to B minus 1, B plus 1. It comes from the linear map which identifies -1 plus 1 as closed segments with B minus B plus as another closed segment. And so then the collection MI WJ is mapped by this real map sigma as L minus 1 of M. So now maybe after I wrote down this formula, we can try to figure out if that's what's happening using this geometric intuition. So so first of all, let's see why M indeed belongs to this. I guess. So we already know that CIs belong to RK times 0 AI times 0 1 n minus K minus 1. That was the premises of this. So MI corresponds to CI. And now we want to see that the disjoint union of CIs actually belongs to this. So I guess this condition is really trivial. The only interesting thing here is this, and to see that it holds, we can try to okay. So we know that Ci in the k plus first coordinate belongs to ai minus 1 ai, segment like this. That's quite clear. Now we also know that we have this inequality b minus b plus aq. So I guess, and let's assume that our configurations are non-empty. Then we have strict inequalities, and then we need to see why the disjoint union of all these configurations really has the coordinate, the k plus first coordinate between these two.
Такой ответ, что ничего не понятно.
Ничего не понятно.
Okay, so far it doesn't seem to be clear how to transform the formulas into pictures, which it often isn't. So well, based on the general philosophy behind this construction, what I said is more or less the only way one can make two components, the leftmost and the rightmost components vanish. There doesn't seem to be any other sensible construction which gives this result.
Yes, it seems that way.
То есть, может быть, там происходит что-то более хитрое, но вот так вот сходу ничего, кроме как угнать две компоненты на бесконечность, в голову не приходит.
Yeah, you're probably right. I mean, that's probably exactly what's happening here, but so I don't know, maybe let's try to sort of make a simulation and see what happens with so my feeling is that actually what's happening is not exactly that the component goes to infinity, rather that the manifold MQ or M1 is compressed into an empty set. So my understanding is that when, for example, WQ goes to 0, B plus just tends to AQ, and now maybe that's incorrect. But then maybe MQ is just compressed into a smaller and smaller, or CQ rather, is compressed into a smaller and smaller configuration, which eventually vanishes. So maybe
well,
I'm not sure.
This I don't think this is continuous. If we have a family of manifolds, then it is continuous if and only if the intersections with every finite pole form a continuous family. Now, if the limit is empty, then basically the only way this could be continuous is that at some point the family ceases to intersect any given finite pole.
Mm-hmm. Okay.
То есть, значит, что-то может стать пустым только уезжая на бесконечность. Значит, если оно все время остается в какой-то конечной области, а потом бабах становится пустым, то есть если значит, возникает разрыв.
I see. I see. Okay. So nevertheless, first of all, let's observe that here, at least to define this map sigma, we didn't require k to be greater than 0. So it equally well works for, obviously, for k equal to 0. So now we just get b minus b plus times rn minus 1. And we can do the same procedure. There is no problem here. I think. Maybe I'm wrong, but it seems that we can do it that way. There is, however, an issue with No, I think it's fine. No, yeah, we don't have any issues, so we can define the map sigma, which goes from BMN0 to CN1. No, this seems okay. I don't know. Does it seem okay to you?
I don't know. I don't know. Saman and Philip, is this okay? Do you agree with what it says on the board?
I'm kind of lost about it, so I don't know.
So you lost it at which point?
I guess in the last 5 minutes, I couldn't follow.
The last 5 minutes.
Yeah, I have a similar issue to Saman.
To be frank, I think we all have this issue because there is nothing to follow here. We have just a formula that somehow should give what we want, but it's not clear why is it what we want really. But
okay, well, let's assume the conjecture I just stated a few minutes ago. If it's any help, if it doesn't help, let's not assume.
well, I mean, the biggest conjecture here is, I guess, that somehow M belongs, or C belongs to this slab as B minus B plus, and this is supposed to be very easy. I don't understand why the statement is true, but it's supposed to be very easy. And I think I don't understand it because I don't understand the meaning of numbers AI here, but I'm not sure.
Well, AI, the AIs are just, значит, видишь, вот эти AI без плюсиков, это, значит, AI без плюсиков, это те числа, которые входят, в конструкцию Мура. То есть AI
да, которые ограничивают К плюс первую координату.
Да.
Но вот
и без плюсиков они понятны. А вот дальше, когда начинаются плюсики и минусики, уже у меня понимание уходит.
Yeah. Ну да, нет, я просто не понимаю, почему там не может быть каких-то конфигураций, которые там где-то меньше, чем b минусик. Ну, как бы, окей. Я на самом деле, я просто вот что, yeah, okay, so I think I understand my confusion. I don't understand how these barycentric coordinates play any role in the geometric picture. That's probably the biggest problem here. So we have sort of separately, we have these AIs and CIs, which come from this monoid, and on the other hand, we have also separately the barycentric coordinates. And what is the geometric meaning of the variation of a coordinate is completely mysterious. So.
And the statement we're trying to prove at the moment is what? Is that the BM something is homotopy equivalent to the next C? Is this it?
Yeah, that's correct. But I don't think that there is a problem with proving this in particular. There is more of a problem with showing that there is this map sigma. So I just don't understand how it works. Then if we have this sigma defined, it is, I think, quite straightforward to prove that we have a homotopy equivalence, a weak homotopy equivalence.
Sigma. Okay, let me have a look. Sigma. Just a moment. I'll have a look and I'll remember what it is. Well, it looks like we just take the so more or less we want to take an element of the classifying space, and then we take just the union of the it's a point of some simplex. And then what we want to do is take the union of the manifolds, which are the vertices of the set. Then there are problems which were just mentioned when one of the when the point tends to either the first phase or the last phase, some of the vertices disappear. By the way, this doesn't happen if a point tends to one of the phases in the middle, because then we just replace the manifold with the union of the two manifolds, and the result is continuous. And when either W naught or W the last W vanishes, then we have the problem. We need to get rid of some of the components which resolve either by using those pluses and minuses, or just by saying let's forget about the pluses and minuses. Let's just chase those components away to plus or minus infinity. So the map sigma is defined regardless of map sigma is defined regardless. By the way, doesn't matter whether or not k is zero. If we have so B M N node is so M N node is the classifying is the monoid of bounded manifolds, of compact submanifolds. Is this correct, Richard?
Oh, it is sort of correct. I mean, strictly speaking, M0 consists of pairs CA, where C belongs to a product like this.
Yes.
No. So, sorry.
Здесь категории, они лежат в ограниченной области. Так, 0,1 будет допустим. Ну, значит, threshold, соответственно, если у нас N1, то им разрешается еще по первой координате быть какими угодно, правильно?
Yeah.
So CN1, this means we allow one of the coordinates to vary from plus to minus infinity, and basically we have the stacking map or the juxtaposition map, which transforms an element of the B into an element of C. So sigma is well defined. I think we don't have any problems with that. It's still well defined. What could break down is the statement that it's a homotopy equivalence. По-моему, с определением сигма, значит, нет никаких проблем.
Okay. So yeah, as Alexei said, sigma can be defined for k equal 0 as well. Now let's show that the induced map on homotopy groups is surjective. So we consider a map like this, which is the obvious map induced on the homotopy groups. And let's represent a spheroid in of degree q in Cn k plus 1 as a map from dq, which takes the boundary of the boundary sphere into the base point of this space, which is precisely the empty manifold. So we can consider a family CT of configurations.
Just another reminder, at some point we will need to have a break. So, Grisha, when do you think it would be best to have a break?
When we will finish this proof.
Well, this part is not entirely straightforward. Let's try to be realistic.
Oh, I want to be realistic. I want to finish this proof and then move on to more combinatorial stuff. So let's do this and then we'll have a break. Okay. So we have a family of configurations which are indexed by the points on the disk, or rather on a sphere. So these are f of t. And we have, so we fix C equal to CT for some specific T. Then the projection is obviously proper because we're dealing with finite configurations after all. And the set of its regular values is just RK plus 1 without the image of this map. So it's open and dense in RK plus 1. Assume that X in RK plus 1 is a regular value. Then the pre-image obviously is empty. Now we can choose an open ball, a closed ball in RK, closed ball, and an interval J in R, such that B times J intersected with PM is empty. So note here that if K is 0, then our ball is just a point. Now we can rescale each ball B times A for A's in the interval to the whole RK times A. Once again, this will be just a point times A. So now we can dampen this rescaling at the boundary of J. So if J looks like this, then the rescaling looks something like this.
Okay. Philip, do you understand what's going on?
Not really, no.
So for a moment, we just consider a specific configuration C, which corresponds to a certain point on the disk DQ. So T is a point on DQ. And then we consider a projection on the first K plus 1 coordinates in Rn. Then the set of regular values is the complement of the image. So we can choose a closed ball in RK and an interval in the complementary coordinate R, so that the product is intersected with the image of our configuration is empty. Well, it's quite clear. If we have just a collection of points somewhere, we can easily choose a small cylinder which does not intersect this collection of points. And then we can consider a following operation on this cylinder. So we rescale this cylinder. So we started from a cylinder. So this is the J coordinate. And this is the B coordinate. And then we just rescale in the B coordinate and we obtain a picture like this. Which shows that after performing a rescaling like this, we see that C can be deformed into C tilde, which is disjoint from the following S of A, which is the product RK times A times 0 and minus k minus 1. So it's a slice like this for a certain for any point A in a certain sub-interval in J. So what that means, well, let's look once again at this picture. Oops. Let's look once again at this picture. What's happening here is that assume that we started from this cylinder and some configuration of points around it. Then, after performing a rescaling like this, only some points remain, other points were thrown out into the infinity. And the remaining deformation of the initial configuration is such that we know that it is disjoint from a slice like this on for any so a slice like this basically looks like RK. So RK is this this direction. Then we have a specific point A here. So point A in some interval J prime. And then we have this constraint which can't be really seen from here, but because we have a 2D picture, and this is the interval in the third dimension.
Philip, does this explanation explain anything?
I mean, I'm following the explanation. What are we trying to show at the moment?
I'm just showing that we can deform C into certain C tilde such that it is disjoint from a slice like this. So
yeah, this is clear, but yeah.
Okay.
The configuration is different.
Yeah, but it is still equivalent. So we have a path that connects C and C tilde.
Yeah.
Because, so now we just observe that for close values of T in DQ, we can choose the same B times J, and this is quite clear because indeed if we have two configurations and a cylinder here, and our configurations wiggles a bit, so maybe it moved around in some small way. Still this cylinder does not intersect our configuration. So this means that we can actually choose a covering by a finite set of open subsets in DQ, because DQ is compact. We will consider a closed disk, and it is compact. So it's a covering. And we have the corresponding collection of JIs for BI times JI. So basically what's happening, the configurations transform on the sphere, but for each part of the sphere, we can choose some fixed cylinder that does not intersect the configuration. Then we can make JI smaller. Can be compressed so that we have a disjoint union of this, and we can also dampen the deformation outside of an open bi times ji.
Okay. Salam, does this make any sense?
Yes, after explaining, yeah, it became more clear. It's fine now.
All right. Let me just show what is what we get in the end. So all these deformations are necessary to obtain a deformed map from DQ. So another spheroid in CNK+1. Not. So since our construction was continuous for small variations of T, and we chose a finite cover, and also we know that this deformation deformation was constant on the boundary, because the boundary of the disk precisely corresponds to the empty configuration, and the empty configuration is preserved by any kind of I don't know, rescaling and anything. So this is really a homotopy between spheroids. So a homotopy between spheroids that are presented as these real relative maps is just a homotopy that does not do anything on the boundary. And now we can choose slices as AI disjoint with CT on UI with AI which belongs to JI. So returning back to this picture, these slices look like this. And maybe something in the third direction, but basically they look like these vertical lines. We can choose WIs using the partition of unity on the covering UI, and over DQ over the boundary of DQ, so over the boundary sphere, we choose the slice S of A, S of 0, with weight 1. So there are no other slices. Now we can choose parts of CT between the slices. So we have a collection of slices, basically spliced the whole space using these things, and we can choose collections of points that sit between consecutive slices. And now we just use this splicing of our configuration to obtain a lift onto the classifying space of B, M, and K. And so because of our choice for the boundary sphere is mapped to the point, And we see that sigma G is homotopic to F because basically because of our construction. So let me explain conceptually what is happening. So basically the idea is that we have this kind of map into the space C and K plus 1. And then we want to sort of obtain a kind of a simplicial map into the classifying space. So to do this, we sort of partition our map in a continuous way and assign some weights to it, so that we obtain the components of this map on various simplices in the classifying space. So that's the basic premise of this construction, and we see that because of this sigma lower star is an epimorphism.
Okay. Well, I suggest we just say that it's the same for a similar argument proves that the map is injected and have a break.
Okay, I'm feeling like I'm holding the attendees hostage with my talk. So yes, probably it's a good idea.
Значит, доклад, который продолжается больше 1,5 часов, это издевательство.
Okay.
Okay, so let's have a break and then we will continue. Okay, well, it looks like 20 minutes are up. So if we're ready, let's continue.
Okay, so by the generous will of LSA, we don't have to prove monomorphy of we don't need to prove the monomorphy of the map sigma lower star, so we can move on to the combinatorial investigation of homological stability for symmetric groups. And let me just once more recall why we are interested in this at all. So a combinatorial approach to homological stability of the sequence sigma m. So as we saw, our methods using the configurations and all this maths and Weiss like arguments essentially allows us only to identify the homology over a co-limit of symmetric groups, which is already a tremendous result, but we actually want to see that we have stability. So in a sense, the previous result is not about stability, it's about some limits. And to do this, we will investigate this sequence directly. So we have a sequence of inclusions where the group sigma n just does not act on the n plus first element of the set of n plus 1 elements. So to do this, we will need some simplicial methods. So let me recall several useful results. So first of all, we have a proposition like this. So we have the category delta plus, which consists of finite ordered sets and injective maps, injective order preserving maps. So it's finite ordered sets plus injective order preserving maps. Or you can think of it as a category of linear categories with finitely many objects and order preserving functors, and just functors which are injective on objects. And it is obviously the subcategory of the usual simplex category. And what is interesting about this inclusion is that it is homotopy initial, which means that if we take the homotopic limit over delta plus, we obtain the same thing over delta plus opposite. We obtain the same thing as the homotopic limit over delta. Sorry, over So the homotopic limit over delta plus is the same as the homotopic limit over delta if we consider the induced diagram. So the practical application of this result is that we can consider semi-simplicial sets instead of simplicial sets, and the geometric realizations will be the same. So if we have a simplicial set, then we can form the semi-simplicial set by restricting to the subcategory delta plus. And the realization of this simplicial set will be weakly equivalent to the realization of the corresponding semi-simplicial set.
Я чуть-чуть потерял нить. Что такое плюс?
Это просто индуцированное, если у нас есть симплекциальное множество, то у нас есть полусимплициальное множество, которое просто получается выкидыванием вырождений.
Ну, плюс это не очень хорошее обозначение, потому что плюс обычно означает прибавление дизъюнктной точки.
Okay.
So this is just the forgetful functor from simplicial sets to semi-simplicial sets.
Yeah. Yes. So more maybe Hybrid notation will be the pullback diagram with respect to the sublution.
Well, a small additional remark instead of simplicial sets, one could consider simplicial spaces, and in which case it is not always the case that there is a homotype equivalence between the geometric realizations, but it is the case for simplicial sets, which are good in the sense of sequel. I will not go into detail. The details can be found in a paper of Siegel. If some of you needs this, please let me know, and I will give you a reference. And by the way,
actually, the fact is that this kind of result holds in any simplicial model category, and I guess the modern reference for this is Emily Reil's book, which is called, I guess, I always forget the order of words. Yeah, categorical homotopy theory. It's one of the basic applications of quantum calculus and stuff like that. But nevertheless, let me just briefly explain why we even care about semi-simplicial sets. So basically, we do care because they are smaller. They're significantly smaller than simplicial sets. So, for example, for semi-simplicial sets, you have this intuition that if something is finite dimensional, then you don't have simplices about certain dimension, unlike the simplicial sets. And it's very convenient to work with semi-simplicial sets instead.
There are two geometric realizations for simplicial sets. There is a thin one and a thick one. Which one are you considering here?
I'm considering the fat one.
So does it take degeneracies into account?
No, it doesn't. It's the essence of the proof that the fat realization is the same as the.
No. That's okay. So if we do not take degeneracy, if we do not quotient out by degeneracies, we get a thick geometric realization. And if we do, we get a thin geometric realization. So let me and these are often, but not necessarily, homotype equivalent. Let me try to remember the statement. Anyway, let's move on. For simplicial sets, not spaces, sets, everything works.
All right. So let me recall the following result due to Siegel, which allows one to compute the homology of the geometric realization of a semi-simplicial space. So the spectral sequence looks like this. We have a homological type spectral sequence. We have a semi-simplicial, so a semi-simplicial space, and the spectral sequence converges to the homology of the realization of this semi-simplicial space. Moreover, we can say that the edge homomorphism of this spectral sequence coincides with the canonical map from X0 to the realization. So the edge homomorphism for a homological type spectral sequence is, I guess, what you get here. So we have the in principle the homology of X0 here, and that's right. Yeah, that's right. And then the infinity of H is here is the certain quotient of this homology, so we get an edge homomorphism. All right, so that's a useful spectral sequence which will apply to study the homology of symmetric groups. But let me just briefly sketch the proof strategy of the Nakalokos theorem, which I formulated last time, which essentially is the prototypical stability result for symmetric groups. So the proof strategy is the following: we replace the universal bundle of sigma n with something sufficiently connected. Then we study, so moreover, this something is obtained as a geometric realization of a certain semi-simplicial space. Then use this Siegel spectral sequence to study the homology of this homotopic quotient of this pseudo-Tettel space by the action of sigma n, and then obtain a certain result on how a homology of the symmetric groups looks in a certain range. So the idea is that instead of the contractible total spaces, we consider something highly connected, also with a sigma n action, of course. Then we take the quotient and we analyze this semi-simplicial space spectral sequence to compute the homology of a symmetric group. Okay, so let's first of all let's construct these total spaces. So first of all, let me give a completely unmotivated construction, which looks like this. So we take the category of finite sets plus injective maps, and we denote it by Fi, and we consider a semi-simplicial set which looks like this. So in degree P, we have the home set in this category of finite sets and injective maps from P to N. So this is just 0P, and this is the set of M elements. So the face maps are constructed by taking delta i's, which go from P1 to P and then dualizing them. So these are just the usual inclusions which miss the element with index I. So this all looks very strange and unmotivated. So let's try to visualize this semi-simplicial sets. So visualizing WM 1 bar. So first of all, let me give the following definition. So assume that V is assume that V is a set, then a simplicial complex on V is a collection of subsets, collection K of subsets in V, such that if sigma belongs to K, this means that so basically that means that this collection is downward closed. So for any subset tau and sigma, tau also belongs to K. So this is somewhat alternative, very classical alternative language to simplicial sets and semi-simplicial sets. These are just spaces that admit very regular triangulations. And of course, we can consider geometric realizations of such combinatorial structures, which are constructed absolutely analogously, or you can even give like a very explicit description in terms of certain unions of simplices in R, the number of elements in V plus 1, I guess. No, just the number of elements in V. So you just take the simplices, which are so you just take the collections of elements in V which span a phase in K, and then you consider simplices which are generated by the ends of the basis vectors which correspond to these vertices.
Let's say if we lost someone or everyone. Saman and Philip, does any of this make any sense?
Yeah, for me, yeah, they're familiar already.
Philip, what do you think?
No, could you just repeat?
Yeah, okay. I think the best way to explain this is to give an example. So consider a set on like 3 elements and assume that we have the following maximal faces. So these red subsets are elements of this collection K. Then obviously all vertices are also elements, and the empty set is also another face of K. So how do we construct a geometric realization? Well, let's just take R3. So we have 3 basis vectors, and let's take the ends of these vectors and just consider simplices that are spanned by collections of vectors which correspond to faces of K. Then we get a simplex like this, a simplex like this, and a simplex like this. So the geometric realization is just a triangle without the interior. So hopefully it explains a bit this conception of the geometric realization.
Yeah, the example is very clear. And they're always unique.
Yeah. I mean, in a sense, if you use this particular way of constructing the geometric realization, then it is unique. But I guess another reasonable approach would be to consider KNs, which are collections of faces which have exactly n+1 vertices, and then take products with delta n, and then take a co-product like this, and then use the usual relation, just like in the geometric realization of simplicial sets. And you can show that these two descriptions yield homeomorphic spaces, and even better, you can probably say that they are like PL equivalent, but I mean, there are probably other ways to construct geometric realizations. So I don't know. Yeah, but at least this is a very concise way of looking at geometric realizations of simplicial complexes. So basically, in a sense, you always just realize the simplicial complex as a subcomplex in the simplicial complex delta, the number of elements in V-1, which corresponds just to the simplex which is spanned by n's of all basis vectors.
In the first case, do we consider infinite dimensional simplicial complexes?
Well, for our case, it's irrelevant because we always have finite. In like my talk, we will always consider finite dimensional simplicial complexes, but definitely you can do that, and you can modify this construction in some way, or you can just use this construction to get the geometric realization. But for us, we'll only consider finite simplicial complexes where V is a finite set. So, yeah, there are some subtleties there, but they're not very interesting to us today. So now let me explain another construction. So given a simplicial complex K, we can construct a semi-simplicial set which will denote by ord of K bullet like this. So it's called the order complex of K. So we just take I0, etc. IP in V P+1 such that I0, etc. IP, when we consider them just as a set, is a face of K, so it belongs to K, and the number of elements is precisely P+1, so we don't have any coinciding vertices. So there is a very basic explanation of what is an order complex. You just take faces, and then you replace each face by all possible orderings of vertices of this face. So let me draw a picture. Given a simplicial complex delta 1, which looks like this. So the collection of faces is 0, 1, 0, 1, and the empty set. The corresponding order complex in the using the usual picture that represents a semi-simplicial set looks like this. So we have the segment was replaced by two segments which correspond to two possible orderings of the set 0, 1. And that's the possible way to visualize this Wn of 1. So we have the following lemma that actually this semi-simplicial set Wn1 bar is nothing more than the order complex of the simplex. And so I guess I'm not going to prove it. It's well, yeah, I'm not going to prove it, but you can sort of see it from the previous description using the home sets in the category of finite sets and injective maps. So a map. Basically, I guess let's just look at the simplices of. I guess maybe I can just sketch the proof. So recall that Wn1 bar P consisted of maps in the category of finite sets and injective maps from a set consisting of P plus 1 elements into the set consisting of n elements, and such map basically just corresponds to a map from delta P to delta n minus 1. So it corresponds to just a simplicial map. But these maps may differ by the order of vertices. So you can have two maps which have identical images in delta n minus 1, but they're different as maps because here we have a different order on vertices. And so this shows that basically, yes, Wn of 1 bar is the order complex of the simplex. So that's the idea of the proof. I'm not sure. Maybe it didn't convince anybody. Is someone still alive?
What's the Euler complex?
The order complex. The order complex is this thing. So we replace each face with all possible orderings of vertices of this face. So like we did here, we had a segment and it was unordered. So we just have a pair of vertices. But this can be viewed in two ways. It's either 0 to 1 or 1 to 0. And so this gives us two faces instead of one. And we can do the similar thing for two simplex. Unfortunately, I'm not very good at drawing like a lot of simplices stacked one over the other. But essentially, what we have is that we have the order complex of the edges glued together by vertices, and then to each combination of edges we have a corresponding two-face. So the picture will be clearly incomprehensible, but hopefully someone will get the idea of what is happening here. So this is a very, very rough picture of the order complex for delta 2. And so on. And here I try to prove that this is actually the same thing as this semi-simplicial set Wn of 1 bar. Okay, so I don't know. Are there any questions here?
Okay, so Martin, Philip, does any of this make any sense whatsoever?
For me, not completely, but I mean, I'm not completely lost, but I'm not completely okay but I guess because I'm just tired. I mean, it's okay. I mean, I'm gonna read back again, maybe tomorrow. So I don't think it's gonna be a problem if I read again.
Oh, for me, it's okay.
Okay, so one more thing I wanted to say about this presentation is that it seems, at least for now, that actually another thing that this WN1 bar is close to is the Milnor construction. As you can see, if we consider, for example, sigma 2 join sigma 2, we will obtain something like this. So we have the identity element, and another identity element. So maybe I should use different colors for different copies of sigma 2. And then we also have the generating permutations and the edges that connect them. So this is the second stage of the Milnor construction for sigma 2. So the Milnor construction in principle yields the total space of the universal bundle by taking the co-limit of sigma 2, for example, self-join n times, and the co-limit for n tends to infinity. So you can see that if we add another copy of sigma 2, we'll get the suspension and the connectivity will rise. So this is indeed a contractible space. But it seems that the order, so this order complex W2 1 bar is actually just a more economical presentation of the same thing. So we can contract the edges between the same elements and obtain the complex or the semi-simplicial set W2. So it seems that there is yet another connection with more classical constructions for universal bundles. And now I want to, well, I guess I don't have much time. I don't know, how much time do I have left?
I don't know. Does anyone else know? I don't know when exactly we're supposed to finish. Well, I would say let's finish at 8:30. No, sorry, 7:30. And then if we aren't able to cover the whole construction, let's do it next time.
Okay. Yeah. So now let me say something about connectivity of this model for the universal bundle. So I claimed at the beginning that WNs should somehow approximate the universal bundle, the total space of the universal bundle for sigma n. So one necessary part of this is that they're sufficiently connected. So the total space of the universal bundle is always contractible, but for us, we want at least some measure of connectivity here. And to see how exactly, so to see how connected these semi-simplicial sets are, I introduce the following classical combinatorial constructions from combinatorial topology. So first of all, I introduced the link of a simplex. So if we have a simplex sigma and k, a face of a simplicial complex, we can define a simplicial subcomplex, which is called the link of this simplex. And the link of the simplex is defined as follows. So we take the simplices from K such that they do not intersect sigma, and the union of tau and sigma is a simplex of K. So this at first might seem a bit strange, but intuitively you should think of it as a combinatorial boundary of a neighborhood of the neighborhood of sigma. So let me draw a couple of pictures. So assume first that you have a simplicial complex that looks something like this, and sigma is just a vertex. And you maybe have something else going on, but it's irrelevant what is going on here. Then the link, so yeah, and we assume that we have filled triangles here. And then the link will be just this collection of edges. So edges do not intersect the vertex at the center, but together with each of these rows edges, this vertex gives a filled triangle. So it's a face of K, hence all these edges belong to the link of sigma. And similarly, if we draw just simplex, tetrahedron, in fact, and we consider a simplex which is just an edge of this tetrahedron, then the link of this edge will be precisely the opposite edge. So, yeah, we have this description, and in fact, we can even generalize this last example in the following lamp, which is probably a good exercise to get a feel for this kind of concept. So a link of a simplex on W for W subset of V is just a simplex on V without W. So this is precisely what happened with the edge here. Okay, so now in terms of this concept of a link, we can give the following definition. So let K be a simplicial complex, and we say that K is weakly Cohen-Moduley.
It's Moduley.
Sorry?
The name is Moduley.
Oh, it's Macaulay, yeah. So it's weakly Cohen-Macaulay if of dimension D, if first of all, the realization of K is D-1 connected, and second, for any K simplex, sigma in K, and for any K greater than or equal to 0, the space which is obtained as a geometric realization of this over link of this simplex is D minus K minus 2 connected. So So the motivation for this definition is initially it initially comes from commutative algebra, where there is a class of rings which has this Cohen-Macaulay property, and there is, in fact, a stronger condition, which is due to Stanley, who originated this term for simplicial complexes, which asserts that, in fact, I'm saying that I'm a bit incorrect here. So the original definition of Stanley is related to certain combinatorial algebra, and I don't want to go into that, but it was later proved by Reisner that, in fact, the Cohen-Macaulay-Maclaurin condition for simplicial complexes is equivalent to the fact that for any simplex sigma in K, the link of sigma is homologically connected for up to this degree. So we take the dimension of the link, and we require that this simplicial complex is homologically connected up to this degree. So let me draw a picture. So, for example, a complex, say like this, is Cohen-Macaulay. So a disjoint union of three segments, and it is homotopy equivalent to a 3-point set, which is not connected in any sense. So this shows that, well, this is just two visual illustrations of this Cohen-Macaulay property. And yeah. So a simple lemma asserts that the simplex delta V is Cohen-Macaulay, or rather weakly Cohen-Macaulay, of dimension the number of elements in V minus 1. It immediately follows from the description of links in the simplex, because obviously any phase in the simplex is just a simplex on a subset of V. So as we sort of asserted earlier, it's a simplex on this, and it's quite easier to see that that the simplex is contractible. Hence, the the weak Cohen-Macaulay condition holds precisely for this dimension. But why do we need this? The answer is quite remarkable. As it turns out, this Cohen-Macaulay can be related to connectedness of the order complex of a simplicial complex. So I guess I don't have enough time, so I will omit one technical construction. I will just state the proposition, which is due to Randall Williams and Weil, who introduced this technique of order complexes for the study of stability for automorphism groups. And their proposition asserts that if K is weakly Cohen-Macaulay of dimension D, then the realization of this semi-simplicial set is D-1 connected. So actually, the proof of this proposition is quite nice, and it just requires some results about about simplicial topology, or rather combinatorial topology, but I don't think that I have time to present it, so maybe some other time. But it immediately follows that since Wn1 bar is actually the order complex of a simplex, we immediately see that Wn1 bar is n-1 connected, and that is, or rather, maybe something like this. This is remarkable, and it immediately shows that Wn1 bar is a good model for the universal bundle. There is one more property that makes this model extremely appealing, and that is that this is a transitive sigma n semi-simplicial set. And what that means is that sigma n acts transitively in each degree. It's quite easy to see because, as we saw earlier, this is the order complex of a simplex, and simplices in Wn1 bar are just various orderings of p element subsets of n. So so this consists of orderings of p element subsets of 1, etc. n. And of course, sigma n acts transitively on p element subsets, which immediately implies this transitivity. And as it turns out, transitive simplicial or semi-simplicial sets have a very appealing property, in that if we consider, for example, just a transitive set, let's forget the semi-simplicial structure, and take the homotopic quotient, or with respect to the action of the group, in our case, sigma n, this homotopic quotient corresponds to the classifying space of the stabilizer of any element in S. So S small is an arbitrary element in S large. Since the action is transitive, all such stabilizers are conjugate, which means that this is a well-defined equivalence. And this particular property will allow us, if I will ever continue this talk, to study the quotients of Wn+1 bar over sigma n+1. So yeah. Because we will see that it is quite easy to identify the stabilizers in certain cases, and the stabilizers themselves are symmetric groups, and that yields various comparison maps between homology of symmetric groups and allows us ultimately to prove the stability result of Nekrolov. I guess I have 2 minutes left, and I think I can stop here. If there are any questions, suggestions, or comments, please.
Let's try to do this the other way around. Philip, what did we just prove?
Did we prove anything?
To be honest, I didn't really understand this last bit about the stabilities. Like,
okay, Grisha, what did we just prove?
I mean, we didn't yet prove anything. I just stated various results and how we can sort of use them to obtain stability, but I didn't, strictly speaking, prove anything.
Okay. How far away are we from proving anything?
Well, we're very close to proving this proposition. So this proposition is, well, it's very simple, actually. But to prove the homological stability of symmetric groups themselves, we will need some quite involved arguments with spectral sequence of the semi-simplicial space and stuff like that. So
let's ask ourselves, do we want, well, first of all, what exactly is the advantage of using this description for as far as I remember, we get a better stability range. Is this correct?
Yes. First of all, we can get the stability range because our previous method didn't give us any range at all. It just gave us the limiting result. So,
I guess one could extract some sort of a stability statement, not just a limit, but then there's using the construction from the first half, but there's no guarantee it's going to be a good one. Well, the next question is, do we want to okay, so perhaps perhaps a sensible thing would be to talk about this in more detail some other time, and to have a talk by someone else next week. What do you think?
Yeah, I'm not sure about. So let me just stop the recording here, since we're discussing this administrative stuff.